All right. So I want to talk about a new test today. It's the last test. It's called the ratio test. I don't want you to get it confused with the limit comparison test. The limit comparison test was the last test that we learned, and it was also a ratio. It was a ratio of two different series as n goes to infinity. Okay, and we said if it's finite and not zero, then either both converge or both diverge. So what's important with the limit comparison test is that you pick a series that you know either diverges or converges. If I'm comparing it to a series that diverges, the limit comparison test is only going to tell me that that series diverges. If I'm comparing it to a series that converges, the limit comparison test is only going to tell me that that series converges. You sort of get used to not very far from now, you'll be able to just kind of look at these and see whether they diverge or converge instinctively. You'll just see enough of them. It'll be like the piano is to Mozart. You can just play, but you do have to step back and tell which test proves it oftentimes. And so the ratio test is one that involves ratios, but it's the ratio of the next term to the previous one. Okay, so S is still this series, this infinite series. So it goes from 1 to infinity. And I'm taking the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And I'm going to call that r. And if you remember what r we've used refers to, r refers to oftentimes the common ratio in a geometric series. And so this is not a geometric series. However, we're talking about, is it converging to a geometric series? If the limit as n goes to infinity of the next term to the previous one converges on a finite number, then that series converges to something that's geometric. And oftentimes these series will converge to something that's geometric. And just like with the geometric series, if that r value is less than 1, you may have guessed it, then S converges. If r is greater than 1, then S diverges. Okay? If r is equal to 1, it's inconclusive and we need to use a different test. So an example of how we use the ratio test, and by the way, a lot of times I get asked this question is how do you know which ones to use? And I think the ratio test is kind of like your last, it's probably your last option. It's like partial fractions are in the different tools for finding integrals. But it's definitely the one, when you see factorial, I would think ratio test. So I'm going to say the sum of k factorial over k cubed, okay? Or, and I guess we're going to switch this to n, but I'm going to divide a sub n as n factorial over n cubed. A sub n plus 1 is n plus 1 factorial over n cubed. All right, now I'm going to go through and I'm going to evaluate this. And so I'm going to put n plus 1 factorial over n plus 1 cubed over n factorial over n cubed. And what you'll usually do is a little bit of rearranging and shifting these things so that you can figure out what the limit is. So if I keep going with this, I get n plus 1 factorial over n factorial. I get n cubed over n plus 1 cubed. Well, you may need to go to Desmos to prove that to yourself, but that approaches 1. As n gets bigger and bigger and bigger, that part approaches 1. If you think of what's n plus 1 factorial over n factorial, well, what's 7 factorial over 6 factorial? Well, that's just 7, right? So this is going to be n plus 1. Okay, so if I'm thinking, does this diverge or converge? This diverges because its limit is infinite. And that's the basic how you would set up the ratio test. And a lot of times there's a little bit more shuffling around of things than I've shown here. But I would just remember that it works oftentimes for factorials and things that we don't have another example for how to do yet.